We need to be able to draw enthalpy or energy level diagrams, and I'm going to look at endothermic first. So for endothermic reactions or any reactions, we are going to assume reactants are on the left hand side yielding products. So R for reactants and P for products, and this reaction is represented by enthalpy or energy change. Rxn for reaction, and this indicates it's at standard condition, 25 degrees Celsius, 1 atm pressure. And we are going to talk about endothermic reaction, so by convention we decide it's positive, bigger than 0. In endothermic reactions, energy is required or needed or absorbed. So energy is absorbed. It's absorbed from the environment or the reaction beaker or vessel. So usually the reaction vessel gets colder. The reactants are somewhere here. They have some potential energy, but compared to their products, they want to make it up here, products. So the difference between product and reactant is the amount of energy they need. They need this much of energy to be able to make it up there. And this difference is known as delta H, or enthalpy of reaction. Then again, you need this much energy to be put into it, so it's bigger than 0. No matter if you're endo or exo, you always have a hump of energy known as activation energy that you need to satisfy for the reaction to take place. Activation energy is the minimum energy needed for reactant particles to collide successfully to give you products. I'm going to give you a couple of examples of endothermic reactions that I want you to sort of remember. So for examples, first I go after states of matter. What happens when you take solid ice, you melt it into water, then you put it on a stove and you boil it into steam or gas. Now, if you imagine solid particles are well packed next to each other, not much kinetic energy and movement, as you apply heat to them, these particles start vibrating and they sort of go away from each other, and there is a flow here. Now if you increase the temperature and make them into a gas, they have rotational and vibrational movements and they go away from each other in gaseous form. So when you melt something and then when you evaporate something, that is example of endothermic reaction. So this process is endo. It needs energy to do that. There are a few other examples. I'm going next slide and I talk about their chemistry and definitions that you need to sort of memorize and remember. So for sake of IB, the first thing you already knew is enthalpy of ionization. You called it ionization energy. It's the energy needed or required to remove 1 mole of electrons from the gaseous atom. For example, if you have sodium gaseous form in a mass spectrometer, bombard it with electron and successfully remove electron. In order to remove electron, you need energy. The reaction Rxn becomes IE, ionization energy, and this is how much energy you need to remove that. 494 kilojoules. So if they won't ask you to draw an enthalpy diagram for this, but here, down here, you have sodium solid, and up here you have sodium gas, sodium gas, and then here you have ion of sodium plus electron as your product. So this is sort of enthalpy diagram for that. Another one that is sort of common sense is bond enthalpy. And the average, I'm going to explain it later on when we need it in calculations. Bond enthalpy could have two definitions, whether you break it or make it. If you break it, you need energy. It's endothermic, and it makes sense. So bond enthalpy could be defined as energy needed to break 1 mole of gaseous covalent bond. Cl attached to Cl in a diatomic molecule is covalent. When I need to break it, I need 242 kilojoules to break that bond. So bond enthalpy is breaking covalent bonds is another example of endothermic reaction. One other word that comes soon at you is lattice enthalpy, and that's the energy you need to break 1 mole of an ionic compound into gaseous ions. If you have a picture of sodium chloride, it's sodium ion attached to chlorine ion, but it's an ionic network. It goes on forever. So let me just give you one phase that has 4 of them attached. This is example of a lattice enthalpy. In order to break them, you need energy. That makes sense. So in order to go from this solid to gaseous ions, you need exactly 771 kilojoules. So this is your reactant and these are your products. Some examples of endothermic reactions that you should know.